Hi everyone, Eric here. I wanted to do a quick video on Gauss's law today. This is it's presented as a pretty complex topic, but I wanted to clear up some common issues people have with it. This video, I'm just gonna mostly just talk about it and do an example problem. This will most likely be a two-part video because there's a lot to talk about when it comes to Gauss's law. But hopefully we can clear up um, some issues and make this easier for everyone. All right, so first things first is let's talk about Gauss's law and why we use it. So Gauss's law is really just Coulomb's law. So Coulomb's law is the electric field E is equal to K Q over R squared. So this is Coulomb's law for an electric field. And I can show you that Gauss's law is the same later. But um, for now, just know that you're not really learning anything new in terms of concepts. You are still solving for the electric field of something, and you're gonna still work with like a charge. The difference between Coulomb's law and Gauss's law, or why we use Gauss's law, is that it's easier to use Gauss's law when it comes to symmetrical distributions. So, for example, if I have a point charge and then another point charge, right? So this one's negative, this one's positive, and then maybe another point charge here, and then my axis is something like this. So this is not a symmetrical distribution. So it's easier to, if I want to find the electric field somewhere over here, then it's easier to just apply Coulomb's law 3 times. So I would apply it here for that distance, and this distance, right? So for that kind of situation, I would use Coulomb's law. Mostly point charges is what you're going to encounter at MSOE. Now, let's say instead I had something that was a sphere, and I wanted to find, and I know that this sphere has some charge, Q. So it has some charge Q. Surprised it didn't let me write that. Oh, it was right. All right. So some charge Q. And I want to find the electric field someplace out here. And my axis is something right in the middle on here. Well, if I can think of this as a radius, r, this distance as a radius, and then I can expand this radius to a full circle around this whole charge. This is now a symmetrical distribution. So something like this, I can use Gauss's law easily. So what the takeaway from here is that Gauss's law is going to be used for systems that are symmetrical, while Coulomb's law will be used for anything else, really. Okay, so now let's talk about Gauss's law, the details in here. So another question I tend to get is, what does this symbol mean, this swirly line with a circle over it? So this symbol, I always take it to mean as they're just telling us the boundaries of our integral. So I don't know why it's scrolling. I think I'm pressing. But if I see this symbol, why is it doing that? Sorry, 1 second. I don't know why this thing is doing what it's doing. that works. But this. Okay. So when I see this symbol, I know that this means to integrate over my entire integrand boundary. So the reason they give you this symbol is when you see that my integral for Gauss's law is with respect to dA, that means a piece of area. So instead, I could also write this, if I'm talking about an area of a circle, I can also write this as a double integral dx dy, which means I have boundaries in the x direction, so I sweep in the x and then I'd sweep in the y. So instead of writing a double integral, they just tell you to integrate over the entire area. So this whole thing is just telling you to integrate over all of your shape, your entire shape. It's a quick way. This will come up again when you have a 3D space so that you don't have to draw a triple integral of dx, dy, and dz or something like that. You would write this and it's a little simpler looking. And if this was like an integral over a volume, you can just say the whole volume with this circle. Okay, so that's what that symbol means. So then we can say that the E here is my electric field. So that's usually what we solve for when we use Gauss's law. It can be given, but this E is the electric field. And then again, this dA is over my entire area. So remember that this is surface area. Yeah, so it's going to be the area of my system. Usually it's a sphere. It can also be a cylinder or a plane, but know that this is the area. And since I have this integral over all of the area, you can generally just substitute in the area when you get to solving the problem. Now the next part is this Q enclosed. So what this means is it means this is the quantity of charge that I have enclosed. So I've circled with my Gaussian sphere. And my Gaussian sphere is going to be like this blue dotted line that I've drawn. So that is my Gaussian sphere. This red is going to be my sphere, my physical sphere. And what's important is the Gaussian sphere isn't something that actually exists, but it's something that we use as a mathematical tool to calculate the electric fields at certain points. So whenever I want to draw a Gaussian sphere or whenever I speak about a Gaussian sphere, it's going to have the radius of where I want to have my electric field, where I want to calculate the electric field. So in this case, my Gaussian sphere is of radius r. I can draw another one where it'd be way out here, right? And this would be lowercase r. And now my radius of my Gaussian sphere is this one. It can also be inside here. Let's call this L. So I can have a Gaussian sphere of radius L inside. But the Gaussian sphere is just telling us where to draw. And what's important to know about that is that it is a sphere. So I've drawn it in 2D as a circle, but you have to be aware that it's a spherical shape. Okay. Um, and then epsilon naught is just a constant. It's the permittivity of free space. So this will always be the same number when you're doing Gauss's law, unless for some reason they tell you otherwise. But for now, just assume Gauss that epsilon naught is 8.85 times 10 to the negative 12. I wrote phi here. Sometimes they ask you to calculate the electric flux, which is represented by phi, and that is going to be the dot product of your electric field in the area. And what this is saying is this basically counts how many electric field lines are parallel to the area. So if your area of your sphere goes out in all directions, right? Again, I don't know why it's changing position. I'll fix that later. It's kind of annoying. So your electric field lines are going out in all directions. Then the flux would be how much of the electric field have you encircled. So that's going to depend on the area of your uh, Gaussian surface. Okay, so that's kind of the quick and dirty of Gauss's law. So we can do a quick one. Let's say that on I have a charge. I have a charge here. A charge. Actually, I have a charged sphere. And this is going to be, I'm going to write it. A uniformly charged conducting. So I'm capitalizing conducting because that's an important point. A uniformly charged conducting sphere of radius, let's say 5 centimeters, holds a charge of 4 microcoulombs. What is the electric field 10 centimeters from the center? What is the electric 3 centimeters from the center? Okay, so we have a uniformly charged conducting sphere. That usually means it's a metal sphere because metal is a good conductor. And to make this crystal clear on how Gauss's law works and why it matters if it's conducting or non-conducting, is that you want to know the location of the charge. As soon as you know the location of all of your charge, Gauss's law becomes much easier because of this Q enclosed. Basically, whenever you use Gauss's law, the first step should be, well, one of the steps should be determining how much Q you have enclosed. As soon as you've determined how much Q you have enclosed in your Gaussian sphere, you can easily work out the rest of Gauss's law. And Gauss's law does become easier as soon as you understand that. So if I have a conducting sphere, what's important to know about a conducting sphere is that all of my where all my charge is located. And the way a conducting sphere works is that the charges want to be on the surface of the sphere. So this thing has a charge of 4 microcoulombs, but all of my charge is located on the surface. So something like this. Okay, so why is that important? Well, now that I know where the charge is, I can draw a Gaussian sphere, this time of radius 10 centimeters from the center. So if this length is 10, my Gaussian sphere would be, see if I can do it. Nope. Control Z. Yeah. My Gaussian sphere would be exactly at that radius. Pretend this is a sphere. It's kind of hard to do. All right, so this radius here is 10. And now I can write Gauss's law. So I've drawn my Gaussian sphere, which is this blue circle of radius 10 around my physical sphere. And now I can apply Gauss's law. So I would write integral of E dot dA equals Q enclosed over epsilon naught. Something else is sometimes I write lowercase q or capital Q. It doesn't matter. They're the same in this case. I just sometimes switch it for some reason. But okay, here's my Gauss's law, and now I can start working with it. So first thing I generally like to do is look on the left side of the equation and solve this integral. So I know I have to integrate over my entire area, and my entire area of a sphere is just going to be the area of a sphere, which is 4 pi r squared. So my integral is going to turn into E times 4 pi lowercase r squared. And what's important to remember is that this is going to be the radius of my Gaussian sphere. So this r is going to be 10 centimeters. Cool. Now I can look at the right side of my equation and figure out what Q enclosed is. So Q enclosed is going to be all of this charge that I've circled. So if it holds 4 microcoulombs, then my Q enclosed is just going to be 4 microcoulombs, right? Because I've enclosed all 4 of my microcoulombs. So that's why it's important to know where my charge is. So my Q enclosed turns into 4 microcoulombs. And then my epsilon is like what I said, 8.85 times 10 to the negative 12. I would just divide this over, and I'd end up with 4 microcoulombs. I'm not going to write it, but 4 times 10 to the negative 6. That's micro. Divided by 4 pi times r squared, where our r is 10 centimeters. So 10 times 10 to the negative 2 squared. And I can get a number here, right? If I just type this in a calculator. 4 times 10 to the negative 6 divided by 4 pi times r squared, 10 to the negative 2 squared. And I get my electric field is equal to 3.18 times 10 to the negative 5 newtons per coulomb. So something I want to point out here is this equation. If I just wrote this in terms of just variables, I would get E equals Q over 4 pi epsilon naught r squared. And if I call 1 over 4 pi epsilon naught, if I call that K, then I get E is equal to KQ over R squared, which is Coulomb's law. So this is why I said before that Gauss's law and Coulomb's law are the same. It's because you can just rearrange Gauss's law and you get Coulomb's law. So you're not really learning anything new. It's just Gauss's law is easier for symmetrical distribution. All right, so we've done part one. You get this answer. Now part two says, what is the electric field 3 centimeters from the center? Okay, so for this one, 3 centimeters is going to end up inside of my conducting sphere because my conducting sphere is radius 5, and 3 is less than 5. So my conducting sphere is going to be somewhere like, kind of hard to aim this. It's going to be something like that, where this radius is 3. So then I can again write Gauss's law. So let's go to page 3. My Gauss's law, integral E dot dA equals Q enclosed over epsilon naught. And this time my A is going to be 4 pi r squared still. My E is going to still be what I'm solving for. So on my left side of my equation, I'm going to get E times 4 pi r squared equals Q enclosed over epsilon naught. Now here's the thing. My enclosed amount of charge is going to be what? Since I'm on the inside of my sphere and all of my charge is located on the outside because of the logic that I said earlier, that means I haven't enclosed any charge, right? There's no charge that I'm enclosing inside my Gaussian sphere. So that means my charge enclosed goes to 0. And then when I solve for E here, I'm gonna have 0 over 4 pi r squared epsilon naught. And that's just gonna be 0. So my electric field inside, so the takeaway here is that the electric field inside a uniformly charged conducting sphere is going to be 0 always. So whenever you get that question of uniformly charged conducting sphere, what is the electric field inside it? It's going to be 0 because of this. You should still show this work instead of just writing 0 because it's important to show your work. But this is in a relatively easy case. So outside of conducting sphere, you're going to get a number, but your Q enclosed is going to be all of the charge inside the sphere. Your electric field is going to be 0. Cool. So before I start screwing stuff up, I'm going to end part 1 here. Part 2, I'll do a different example of Gauss's law and maybe go into even more complicated things. This might even be a 3-parter. But that's part 1. Hope you learned something. Hope you're staying safe. We're still being quarantined. Social distancing is a thing that's happening. So good luck out there. Hope everything turns out well. See you guys later.